In this session, we want to deal with the TM wave instant on a conducting boundary at an angle. And so let's first look into this scattering configuration. On the right-hand side, you have a piece of perfect conductor. And on the left-hand side, it could be vacuum or a piece of dielectric material. And the plane of instance is defined to be formed by this unit vector of the wavefront and the surface normal vector. So the plane of instance in this configuration is the xz plane. And we set this plane to be at y equal to 0. And for TM wave, the magnetic field is going to be transverse to the plane of instance. So in this configuration, the direction of the magnetic field is along y direction. So let's first write down the expression of the transverse magnetic field, because you only have one component. It's easier to write. And you also know the propagation direction by knowing this instant angle theta I right here. So you can write down this expression quickly. And in fact, from this side, you can also see that the wave propagate with a component along plus x direction and plus z direction, because you have minus jkx right here, telling you the direction is along plus x direction. And then you have minus jkz here. It tells you that there's a component propagating along plus z direction. And once you know the magnetic field expression, then you can also write down the instant electric field by using this formula. And once you do the calculation properly, you're going to see that the instant electric field will have two components, one along x direction, the other along z direction. Or you can just look into this diagram and you see that this electric field on this plane of instant will have the component along x direction and along minus z direction, which is this term. And the phase term turned out to be the same, because both components propagating along the same direction, because they belong to the same instant wave. Now you can also write down the field component for the refractive wave. And first you write down the magnetic field for this TM wave, because you only have one component along y direction or transverse to the plane of instance, and this component is along y direction. But this time, you can see that the component is propagating in the minus z direction and plus x direction. So you have the minus jkx and you have plus jkz in this phase term. And again, just use this formula. You can also write down the expression for the refracted electric field. And you have two components. And you need to be careful that the component along z direction, this component, is the perpendicular to this surface. So this is the normal component of the electric field at this boundary. And for this, the x component is the tangential component of the electric field at this boundary. And this is quite important to know, because next page will start to match the boundary conditions and figure out the unknowns. And I just say that the tangential component of the electric field are continuous across this boundary, but this is the piece of perfect conductor, no field inside. So this means that the tangential component of the electric field on this boundary has to be equal to 0. So let's write down the instant field and also the refractive field for the electric field. And then identify the tangential component on the surface, which is a component along x direction. So you add these two terms together to get this term and set it to be equal to 0 to satisfy this boundary condition. Then we have to deduce the physics from this expression, because again, there are more than one unknown in this single expression. And again, I want to remind you that a wave must have a wavefront everywhere, every time. So at the boundary, the wavefront have to be continuous. So this phase term have to be the same in this expression. If we set the phase term to be the same, again we recover the Snell's law of refraction, which tells you the incident angle is equal to the refraction angle. With this, you can start to construct the relationship between the incident magnetic field and reflected magnetic field, which is the equal amplitude from this expression. And I want to remind you that when we deal with the TE wave, we end up having an expression that is the reflected electric field is 180 degree out of phase with the incident electric field. But now, in this TM case, you don't have such a 180 degree out of phase. That is because on this surface, the magnetic field is maximum because of the surface current. But in the last case, the electric field on this surface, the tangential component of the electric field on this surface has to be equal to 0. So that's why that you have this case, the HI and HR are in phase. And with the conclusion we have from the last page, now you can get the expression for the total magnetic field by summing the incident magnetic field plus the reflected magnetic field. Then you come up with this expression for the phasor of the magnetic field. And again, you can turn this expression into real expression by multiplying this phasor expression with the exponential j omega t, and then take real product of it. Then you have this real expression. This real expression have two terms. The first term tells you a traveling wave along x direction. And that is because you send a wave from bottom and then reflect it upward. So you can see that there's a component of the energy propagating upward. Therefore, you have a traveling wave along x direction. On the other hand, along the z direction, you form a standing wave because this term is independent of time. And this is the tangential component on this surface. So if you have a tangential component of the magnetic field on the surface, then you can induce a surface current on this surface. And turn out that if you set z equal to 0 for this cosine term, you will get a maximum magnetic field on this surface because of the surface current induced on it. Now, you can also calculate the total electric field on the left-hand side. On the right-hand side, again, it's all 0. And on the left-hand side, you add these two components together. But be careful that you have x component and also z components. And if you sum these two together, then you will also have a propagation term right here. It tells you the wave will propagate along x direction. Right here, it's minus jkx. So you have a propagation wave along x direction. But along the z direction, you have a wave in this direction and also have a wave reflected back. So you have a standing wave term right here, which are independent of time. But there are two components. You have x component, which is the tangential component on this surface, and z component, which is the normal component on the surface. And this is the perfect conductor. You'll be expecting to have some surface charge induced on this surface from the normal component of the electric field. Therefore, if you set z equal to 0 right at this boundary, you will get a maximum value for the normal component of the electric field. But the tangential component of the electric field is equal to 0 because the electric field is inside here is equal to 0. So if you set z equal to 0 at this boundary, the tangential component of the electric field is equal to 0. And so this is the result from this expression. Now let's look into the power flow. By now, I think it's clear to you that if you have this scattering configuration, you send a wave from bottom and then you have the reflected wave upward. And you'll be expecting that the power will flow along x direction because you have the traveling wave along x direction. And you won't get any power flow in this direction because of the standing wave along this direction. And we can also see this result from Poynting vector calculation. Now, for TE wave, you have the y component for the electric field, and you have two components for the magnetic field, one along x direction and one along z direction. If you want to calculate the power, the Poynting vector, the average power flow, you multiply this together and take complex conjugate for the magnetic field and take real product of it divided by 2. It turns out that you only have one component because when you take real product of it, this term multiplying with this part will not give you any real number because you see GA in front of it, and this is there's no GA in front of it. So it turned out that the multiplication of these two is just a pure imaginary number. So the multiplication of these two terms will give you nothing. The power flow will come from the multiplication of this term and this term. Because this GA and GA multiplication will give you -1, and when you take real part of it, you'll come up with some value here. So this tells you that indeed, with this scattering configuration, the power is going to flow along x direction, along this direction. Well, you can do the same calculation for TM wave, and turn out that this term multiplying with this term will give you nothing if you take real part of it. So you also reach the same conclusion that the power will only flow in the x direction. So this is quite consistent with our physical intuitions. 所以呢，最后我做一个这个结论。对一个这个 TM 的 electric transverse magnetic wave 来讲的话呢，它是一个波，这个波呢，它的磁场是垂直于这个 plane of instance。那当这个你有一个这个波相对于一个金属的界面，然后有个角度打过去的话，那它在这个 surface normal 的方向呢，会有一个 standing wave， 然后在另外一个这个plane of instance 的这个垂直方向上头的话，会有一个 traveling wave。那Snell's law of refraction 的话，告诉你说这个 instant angle 会等于 refraction angle。那同时呢，在这个金属的表面，你的磁场会是最大，因为这个磁场呢会形成一个表面电流在这个金属的这个表面上头。那这个是我要做的一点这个复习谢谢。